Okay, folks, we're going to get just a little bit more complicated with some math here. So we're going to be all good, and we're also going to unpack this more in our live lecture. So 1.4, be familiar with the Boltzmann distribution and molecular partition functions. Okay. So, and again, this is only an introduction to the subject. We could make a whole semester's course out of this material if we wanted to. So we're going to start with two constraints, that we have a constant energy and a constant number of molecules. The way that we can express that in these mathematical equations is the following. So for constant number of molecules, we can say I corresponds to state I, so that could be the ground state, excited state, whatever. And if we sum up the number of molecules in all of those states, we end up at the total number of molecules. So similarly now, if we take the total number of molecules that contain energy eta, so that's the energy of the individual level, and we carry out this sum, we will then arrive at our total energy. So we can put all of this together in what's called a molecular partition function, which is our calculating tool for our population of states. So the partition function gets the letter Q, and it says it is the sum of all states. So remember, that could be 1, 2, 3, 4, 5, 6, etc. And it's the sum of E raised to the power negative beta times the individual energy of that state. So beta is 1 over K Boltzmann times T. Okay. So, and now if you recall, the units of K Boltzmann are joule per Kelvin. Temperature is Kelvin. So this gives me a unit of 1 over joule. So in order to use an exponential in a calculation, it has to be unitless. So that means if my beta is calculated in units of 1 over joules, the energy of my individual state has to be in joules to make those units cancel. We could, if we wanted to use the energy of our state in something like nanometers, like the wavelength of the transition, or even wave numbers, or electron volts, or any energy unit we can imagine, our beta term has to be the reciprocal of that energy unit, okay? And so now we finally can put all of this together in the Boltzmann distribution. And so the Boltzmann distribution will give us the population expressed as a decimal of the number of molecules in any state compared to the total, right? So Ni recalls the number of molecules in any state I, and N is the total. So Ni over N gives us the fractional population of that state. And you can see now that is equal to E raised to the negative beta times the energy of that individual state divided by the sum. Well, recall the sum is just that partition function, right? So all we need is the total value of the partition function, which we're going to have to work through in the next slide, and the individual energy of a state. And based on the temperature of that sample alone, right? Remember, beta is a placeholder for temperature, 1 over K Boltzmann temperature. That would give us the fractional population. Similarly, if we wanted to compare the number of molecules in state I compared to state J, we don't need to sum up all of the total. We just need the individual exponential calculations right there. So it'd be E to the negative beta energy of state I divided by E to the negative beta energy of state J. And recall through our exponential tricks, instead of doing that as a ratio, we could take that as a subtraction in the exponent, right? Just from doing the algebra. Okay, so how are we going to deal with this sum? It might seem like, okay, well, just add them up, right? Add them up each time. Well, if we have a large number of states, that would become cumbersome, right, to take this entire summation. So in PChem, we want to look for shortcuts for calculations. So we're going to expand this sum and see if we can't find a shortcut. Okay. So what we have here now, if we just go to our fictitious generic energy level diagram, where we've got evenly spaced energy levels and their corresponding energies. So at the ground state for now, we'll just say call that 0. At level 2, we'll call that eta. At level 3, 2 eta, and so forth. So you can see each of these levels are spaced evenly by this amount, eta, whatever that amount is. Okay? Or I'm saying that wrong. That's the Greek letter epsilon. In any event, energy. Call it E if you like. Okay. So we can start to take this sum by saying Q equals. So if we take e to the negative beta times the energy of level 1, we can see it's 0. So e to the 0 power will just be 1. Okay. So let's do the next state. So that's going to be e to the negative beta times that value, epsilon. I'll use the correct name of the Greek letter this time. And if we keep going on the sum, we're going to get e to the negative 2 beta times epsilon. And if we keep going to the next level, e to the negative 3 beta epsilon. And so you can see if we wanted to do this across a great number of states, this would become tedious. Well, as it turns out, this equation has the functional form of a Maclaurin series expansion. And we might not have recognized that right away, but that is the game that we're going to play in PChem, is trying to find simplified versions of our equations. So a Maclaurin series expansion can be rewritten as the following. 1 over 1 minus, and it would be x if this was like 1 plus x squared plus x cubed, right? That's our normal Maclaurin series expansion. Instead, this is going to go 1 over 1 minus e to the negative beta times epsilon. And so we can now substitute this equation Q into our Boltzmann distribution and thus write the population of any state I is equal to e to the negative beta epsilon of that state I over Q. And now, of course, substituting the result in that we got for Q, we get the following. Pi equals, and I'm going to write this as the following. Let's see here. Oh, it's Q, so it's going to go 1 over 1 minus e to the negative beta times epsilon. So that's just going to become 1 minus e to the negative beta epsilon, where now that epsilon refers to the total energy, right? And in this case, it's just the energy between levels, right? So the difference between 2 epsilon and epsilon is epsilon. But now we've got to multiply it by e to the negative beta times the actual value at that level. And so this will give us a useful equation for actually calculating the individual population of any state, assuming they have this linearly spaced pattern. And we're going to get into those calculations in the live lecture. So if we take a look at some sample calculations here and we compare what a low temperature might look like compared to a high temperature. And again, here we have like the different energy levels, level 1, level 2, 3, 4, 5, and on, okay? So we can see here the total value of Q given a temperature, whatever that temperature is. And now we can see the value of beta times epsilon at those temperatures as well. And what we should recognize here is as the temperature gets higher, we get more population in the upper lying states, which is exactly what we saw in the 3 postulates we proposed. And if we take these calculations and flip them on their side and plot them versus energy level on the x-axis, okay, so that would be level 1, level 2, level 3, 4, 5, and so on and so forth. And the population we get from this equation, I'll put this down on the y-axis, here we get the very famous Boltzmann distribution. Okay, so I had mentioned earlier that we might get some kind of a bell curve. Well, it's not a bell curve because it doesn't, you'll notice that it's not symmetrical, right? It's heavy on one side. So that is what we call the Boltzmann distribution. And we're going to be playing with these Boltzmann distributions ad nauseum this semester. Okay, folks, I'll see you in the next one.